All right, now that you've reviewed the Not So Lost in Space and you went ahead and read the introduction and the purpose of this, as well as the procedures, I want to kind of go over a few things. This can be a very difficult lab for the students, especially when it comes to scaling. Scale models is a difficult concept just because it involves math, and them understanding how to scale something down proportionally correct really takes a lot of work. So I want to go through this with you to help you understand these procedures and how the students are going to scale properly on their actual sheet right here when it comes to taking each planet and then figuring out with the given diameter of each planet, figuring out the scale diameter, and then we're going to do the scale distance in meters for a model based on the actual AU distance of each planet from the sun. So let's take a look at that here. As you can see up here on the board, I already have diameter. That's the first thing that the students are going to be asked to figure out based on the procedures. Our scale ratio that they give us in this lab activity is 5,835 kilometers equals 1 millimeter in our scale model that we're creating. So what you're actually going to do in order for the students to understand this, and I would show this to them on the board, I would do this as what we would call an I do, where the teacher does it first, the students watch, they copy it down. So you're going to take the actual diameter of the planet. In this case, the actual diameter of Mercury is 4,878 kilometers. And what they need to understand is this is it. This is your mathematical equation every time. You plug the actual diameter of the planet and you're going to divide by the scale ratio, which is 5,835. So when I put this on here, and I divide that, you're going to get your answer, and our answer is going to show up as 0.8359. Now you're going to want to tell them, hey, go ahead and round to the nearest thousandths place. The 5 tells the 3, move up, buddy. And it becomes 0.84. And the students will record that on their sheet right here where it says scale diameter. So it'd be 0.84 millimeters would be the scale diameter of Mercury. And then what I would have is I would have the students then do Venus, plug in the actual diameter, divide it by this, and they would do that as their group is there, like together we do. All right, so what we're going to take a look at is Not So Lost in Space. You should have already had an opportunity to look at the procedures and the opening to Not So Lost in Space. If you're feeling overwhelmed, don't worry. That's how most people feel. But what we're going to do is we're going to give you some tips and tricks when doing some of this math so that your students don't feel that way and you feel more confident going forward. Now, if you've already watched the first part of this video, we already went over the scale diameter. What we're now going to look at is what's the scale distance of all of our planets. So what they gave you in your procedures is a scale ratio, and the scale ratio that they asked you to use here was 1 AU equals 25.63 meters. So we know an astronomical unit is the distance from the sun to the earth. Well, in this lab, we're going to take that distance, and this is what we're using it towards in order to create our scale model of the solar system. Now, here's the formula that we give you. The directions don't do a very good job of kind of telling you how to apply this formula, but if you do it this way with your students and you teach it to them this way, we always like to do what I call an I do, we do, you do. So like I, as the teacher, I'm going to do the first one for everyone in the class so that they know how to do it. Then the second one, I would let them do it. So let's take a look here. Here's the formula. And I would have the students write this down. Planet distance. So every planet that you have and their distance, which if you remember looking at this, all the planets' distances are right here on this second column right here, okay? We've already done the diameters. Now we're going to take a look at the distance. So if Mercury's scale distance is 0.387 AUs, all I have to do is just plug in whatever that planet's distance from the sun is, and then multiply it by 25.63 meters. When I do that, which here's Mercury, 0.387, times 25.63, I get this, which is 9.918, and you're going to have them round to the nearest hundredths place. So the 1 will say to the 8, what's up, buddy? And the 8 tells them, move up, buddy. I have my students do that. And then 9.92 is our actual answer that we'll record onto our data table for scale distance. Then I would demonstrate that. The students would write that down. You'd go to your next one, which would be Venus. We could plug this one in, and I'd have them do this at their tables. The 0.723. Have the students go ahead and solve this. So that's going to be multiplied by the 25.63. Have them get their calculators out. Go ahead and solve it. And our answer is going to wind up being 27.63. It's always great to allow a student to maybe come up and give the answer on the board or share a few answers. And when we get our answer here, we'll have 18.530, and that rounded will be 18.53. And that's our answer. The students would record that in the scale distance column right here, and then they just continue on. It's a great opportunity while they're doing this for you to move around, have them working in groups, checking their answers, making sure that they're doing okay. But also, if you need to pop to that group that needs a little bit more help, this allows you that opportunity. When you have this up on the board, they've written down their formula, they know what they're doing, and they all have calculators. So the next part of this video that we're going to look at is after they've completed this table and they have the diameter and they have their distance, now they're going to take it to the next step, which is creating actual scale models out of clay of all the planets, and then going out into a hallway or an open area outside of your school and creating the scale distance of each of the planets. So all right, now we've reached the part of Not So Lost in Space, where the students are going to create a model of all the planets. Now, some of the things that you're going to need for this is going to be modeling clay. I know that your teacher thriftiness says, oh, we'll just use Play-Doh. But Play-Doh dries out and you lose the consistency, especially if you need to extend this another day. So really recommend using actual modeling clay. This is kind of what we use. It's a Crayola modeling clay. I think even the Dollar Tree sells a little modeling clay that you can buy as well. And you don't need a lot to cover all of your classes. We also recommend having toothpicks. That's for the students to be able to put their model planet on once they create it. They're also going to need a ruler. These clear rulers work really well for the students to be able to place it on the top of the centimeter side. Now, one little tip. Students get confused all the time about this. They look right here and they see the mm next to the 0, and they assume that these numbers are millimeters. They're in centimeters. The little smaller lines in between the 0 and the 1, those are the actual millimeters. And it's very important to make sure that your students know that, or else they're gonna be like, we don't have enough modeling clay. Yeah, because you're measuring in centimeters, not millimeters. And then either a piece of cardboard, kind of like we used, or a heavy-duty piece of cardstock is what we would recommend. But here's kind of what the final look of this is going to be. Notice that once the students have their data here, okay, they're going to take that scale diameter that they solved earlier, and they're going to create, using the modeling clay, each one of these planets here based on that. So Mercury here, which you can barely even see, the reason you can barely see it is it's not even 1 millimeter, it's 0.8. So Mercury, then you have Venus, which is a little bit bigger at 2 millimeters. Then you have Earth, which is slightly bigger at 2.1. You have Mars at 1.16, so notice it got smaller. Then you have Jupiter, which is a noticeable size difference, and the students will see that, and they'll know, okay, Jupiter is the largest planet. It has a lot of mass, and it's 24.4. Saturn, which is 20.6. Uranus, Uranus at 8.7, and then you have Neptune at 8.3. But this is a great way for your students to demonstrate this. So if you have them broken into groups and each group is making their own planet model, once they get done, if you have this set up, they can come and stick their planet in, and they're basically creating a whole scale model of all the planets. Now, we talked a little bit about Marzano strategies. Some of the things right here, you're engaging students to move around and interact, which is a great Marzano strategy. They really enjoy that. You're using physical movement because they're going to want to get up, they're going to move around. You're organizing the students to interact, and you're kind of providing scales and rubrics when they're using this and they're seeing how they're working through this. The next part, once they have this all done, is to go and find that large area, either outside or in your school, and you're now going to use that scale distance from the sun, and you're going to place all the planets their distance away from the sun. So take that out, take a look at that in our next video here. Alright, so welcome to the last part of Not So Lost in Space. As you can see, we've taken you outside of the classroom today. We've taken you to a park. If you have a large parking lot, football field, large area, or even just a large hallway in your school, is a perfect setting for this last part of Not So Lost in Space, where you actually model the distance of the planets from our model sun here, which is used as a basketball. You can easily find a yellow basketball on Amazon. That way it has that yellow look. But we're going to show you this today. The students would have their sheet where they figured out the scale distance from the sun in AUs and transferred it to meters based on what they did in the class. It's good to have your models with you, and by having them like this where they're put into a piece of cardboard, it makes it easy to carry. So we're going to give you that perspective today and let you see how cool this activity is for the students, just to see really how far each planet is from the sun and what it looks like compared to the sun. So our first one is Mercury. It is 9.92 meters away. We have our measuring tool. You could use the string measuring tape. In this case, we have a digital measurer that's set to meters. So we'll start right here next to the sun. For your students, they won't have to lean over as much. And we're coming up on our first one. And right here. So right here would be 9.9 meters from the sun, which is the distance that Mercury is away. This is Mercury. You can barely see it, that white. And then there is the sun over there. We'll now go to our next one, which is going to be Venus. It is 18.53 meters away. One important thing is make sure, like if we were doing this at school, we would have a student stay there with Mercury holding it. But since we're out here by ourselves, we'll take it with us. And start exactly from where you left off. You don't have to reset the measuring tool. So we're going to go to 15.8. And here we are. Or 18.5. My bad. I switched up those numbers. Here we are. So right here at 18.5, we have Venus. So you can see Venus here, and you can compare that to our sun. Once again, you'd leave a student here with Venus. We'd pick up and look at our next measurement, which is going to be Earth at 25.63. 25.63. So we continue. Now you're probably saying, it doesn't measure all the way to the hundredths. You might just round to the tenths based on the measuring tool that we have. So here is Earth. We're at 25.6, and I will go ahead and hold this. You can take a look at what Earth looks like compared to the sun. This is a great time to mention about how the moon and the sun appear to be the same size because the sun is 400 times farther away and the moon is 400 times bigger. It just goes to show you that as we're getting farther away from that sun, it keeps appearing to get smaller in our video. So we'd leave a student here with Earth, and now we'll move to Mars, the fourth planet, which is 39.3. So we keep on going. And we're here at 39.3, which is where Mars would be located, which a lot of students are very interested in Mars right now because that's the next planet we're gonna try to go visit and send humans to with the Orion project. But here is Mars, the red planet. You can see the sun has gotten much smaller as we keep getting further away. So notice we are 39.3 meters from the sun right now. Watch what happens when we go from our terrestrial 4 planets, which is what we just hit, to when we go to our Jovian gas giant planets, which our first one is Jupiter. And that distance is 133 meters. This is where your students are really gonna say, wow. So let's get going for this one. Gonna take a little while of a walk. It's always nice to have the students that are back there holding the terrestrial planets because it really makes it a good visual to see just how far away the gas planets are from those terrestrial planets and how close those terrestrial planets are to each other compared to the gaseous planets. So as we keep on walking, we're getting closer. We just passed 70 meters. We still got to go to 133. So you can understand why you need a pretty large open area. If you're at the school, a football field is a great place. You should be able to hopefully get one of the coaches or someone to let you use it. They can be picky sometimes about their football field. But we just hit 100 meters. We got a little bit further to go. But this is a great visual for the students just to see the scale, distance, and size, as well as compared to the sun. Across 115. And coming up on it now, 133.35. And we're gonna stop right here. All right, so we have Jupiter now. This is a great visual. This is our largest planet. It also has a storm raging on it that has been raging since we've known. And you can see the sun all the way back here compared to Jupiter. It's gotten a lot smaller, a lot smaller. So for some of you, this may be the point where you have to stop. You can't go any further, which is still okay because the students get the visual of what's happening, and then it would be a good point to mention how far away the others are. But because we are so lucky, we have more space. So you would leave a student here with Jupiter, and you would get ready to go to Saturn next, which is the ring planet that most students know, and it is 244 meters. So we just went to 133. Now we're gonna go over another 100 meters just to get to our next one. So 244 is where we're going. It's gonna take a little while. So we have hit 244 meters. This is where Saturn would be on our scale distance. So take a look. Here is Saturn. And that yellow dot that you see so far away back there, that is our model sun. Now think about how far we just traveled from Jupiter, and this is the next planet. It really makes a great perspective to think about how the terrestrial planets are so close, but our Jovian gas giants are so far away from each other. So you would leave a student here. They could see all the other students at this point, which would be really cool, and they could see what the planets look like from this vantage point. So the next one would be Uranus or Uranus, and it is 491 meters away. We are going to attempt this one and see whether we can make it happen. So we're basically gonna double what we have right now to try to get to this one. So we'll cut it off so you don't have to stay this whole time, and we'll pick it up when we get to that next spot. All right, welcome back. We have made it to 491.7 meters. So take a look here. Oh, bring it back just a hair. There it is, 491.7. This is the scale distance of our Uranus or Uranus to that scale sun, what you probably can barely see now. This is a great visual. If you can somehow get an open area this big, it's a great visual for the students to be able to see. Because you can now imagine all of your students back there holding theirs. You can barely see them. You can imagine where Saturn was and what it looks like. And this is Uranus or Uranus. Now, you might say, well, I don't have that at my school. You could easily use your track to do all of the planets. Now, I'll show you, we can't go any further because we are bumping up against some trees. And our next planet would be Neptune. And according to our data, Neptune would have to go all the way to 771.64 meters away. There's no way for us to be able to do that here. We'd have to get on the road, keep going down, and we'd have to go at least another close to 300 meters just to get to where Neptune would be. And you can imagine at that point, the sun would be almost like invisible. You couldn't even see it because it's gotten so small and it's so far away. But this, like you can see, is a great visual of our solar system and the sizes of our planets compared to the sun, as well as their distances away from the sun in astronomical units. So this is a great way, based on the Marzano strategies, to get